Right, we are back into our last segment of this very special broadcast from my living room. I hope that you've been enjoying the show so far. I hope that you've been keeping your hands washed in between, that you're washing your devices. We are going to get back into that exam question. We're going to take a look at how to deal with isomers, how it affects their properties, and let's go for that. Before we went away, we took a look at how to rearrange pentan 1-ol. Another way I've seen this mistakenly rearranged is what happens if you just draw carbons like this? Have I actually made an isomer? Well, here's the problem, is that people forget that you can count carbons around corners. If you can count around corners, that means that you've still got 5 carbons in your longest chain, and unfortunately you still have pentan 1-ol. These are some of the common mistakes that I've often seen in exam questions, and sadly, that's not going to work out well for anyone. So when you are starting to do this, please make sure that you are kind of coming up with a different molecule. You're following all of your naming conventions, and you're going to come out with a fully different carbon chain. So the last and really, really nice part of this is where we're going to see the microscopic go all the way up to the macroscopic. And here we go. So we had these learners that decided to investigate the factors that influence the boiling points of alkanes and alcohols. In one of their investigations, they determined the boiling points of the first 3 alkanes. So remember, that is methane. Okay, so methane, ethane, and propane. So those are your first 3 alkanes. Really, really important to know that. And they decided to investigate the boiling points of these 3 and see if they can get some sort of trend, some sort of explanation as to why it changes from one to the next. Now, I don't know if you can see that methane, ethane, and propane have got very different microscopic structures. So this will influence the investigative question. Remember that the question has got to have both independent and dependent variable. This question is for 2 marks. I don't know, you can't really see that on here. You've got to have your independent and your dependent variable. So what I've got to do is, okay, well, what is changing? What is the thing which I change? That is the independent variable. Okay, so does the length of a carbon chain influence the boiling point, which is a dependent variable of a substance? So that is a good investigative question. It should have independent and dependent variables and state them together. Now, fully explain why the boiling point increases from methane to propane. Well, this is where the meat of this question comes in. So let's draw them. And let's apply the knowledge that we've been gaining through the first 3 segments of the show. So methane is the smallest of the 3. Okay, all the way up to ethane, and then propane. The reason I like organic chemistry so much is because it's kind of like shapes and drawings. It's not too much formulas. This is definitely one of my first loves. I've actually drawn that too short there, sorry. I got too carried away. Let's make that into a carbon chain. Okay, right, so there we go. Propane. And organic chemistry is all about patterns, which I particularly like. So ethane. Now, the difference between all 3 of these is the same. All that is happening is I'm making the same thing bigger and bigger and bigger. So methane, ethane, and then propane up at the top. Okay, methane, ethane, propane. First, I need to decide if they are polar or non-polar. Remember, if something is non-polar, London forces are the strongest it's got. If they are polar, dipole-dipole. If it's got OH or NH, hydrogen bonds. This is how you decide the boiling points, melting points, viscosity, if they mix. That is the starting point. Okay, so hydrocarbons like ethane, methane, and propane have got the first requirements. Carbon-hydrogen is a slightly polar bond. I mean, you can prove it if you really want to. But we've got 2.5 over there, 2.1. It's a very slightly polar bond. But I hope you notice that carbon is going to balance out those dipoles, and that all 3 of these are going to be non-polar. They're just like fats or lipids. They are non-polar. That means that there are London forces Okay, now London forces, sometimes called temporary dipoles. Now you can call them temporary dipoles if you like. It's really important that you say that these are very, very weak. They are weak forces of attraction between the two. And that means that it requires less energy to pull these molecules away from each other. Okay, but now here's a question, is why does the boiling point increase from methane to propane? So they all have exactly the same type of intermolecular force. So there's an increase in boiling point from methane to propane. Why, for instance, would a small molecule boil easier than a larger molecule? Well, there's a few factors in play here. Okay, so as we go from methane to propane, let's just list the trends that happened. Okay, so now from methane all the way up to propane, let's list the differences. Okay, methane has got a very low mass. Why am I talking about the mass? Well, the mass matters when you're trying to vibrate molecules. A low mass makes it easier to vibrate molecules. Also, they have a small electron cloud. Really super important to be able to talk about an electron cloud if you're talking about London forces. They also have a smaller contact area. Now, how much of a molecule touches the next one is going to decide how strongly they can attach to the next one. If they've got a much larger surface area, it means that they can touch each other in more places. That means that there's more place for those sticky electrons to stick together. So all three of these factors will increase as you go from methane to propane, and all of those will increase the energy required to pull them apart. So now when you are starting to deal with boiling points, melting points, and viscosity, you need to talk about the energy required to move the molecules around each other. That is the most important thing, because when particles are vibrating, the things holding them together are those intermolecular forces. How strong they are, how much area there is, how much mass there is in the molecules, those are all three factors that you can get marks for. In fact, you could actually make this out of 7 or 8 marks if you fully explain it from that point of view. They only wanted 3 marks in this particular place. Not particularly important to completely over elaborate, but really important to completely cover your bases. We're going to get into the last little segment of this. Now we find that the boiling point, now they're starting to deal with the alcohols, of propan 1-ol is higher than that of propane. I'll explain this observation by referring to the type of intermolecular forces present in each of these compounds. Right, this is an absolute bonus of a question. So what we're going to do is we're going to draw out these two molecules, look at the microscopic, work our way up to the macroscopic, as I've been saying to you. Okay, so they wanted us to compare propane to propanol. So here we go. So propane first. And they said that that's got a very low boiling point, and propanol, propan 1-ol to be specific. Right, let's draw these two and see if we can find the differences in their structures which give away the microscopic to give the macroscopic. So propane, 1, 2, 3, 1, 2, 3, exactly the same backbone. Propane is just got hydrogens. Take a look at that. I wonder if you can see exactly which type of intermolecular forces we've got, because they want to know the names of them and their relative strengths. Propan 1-ol means that the ol is on the first available carbon from one of the chains. You can draw it on the left or the right as long as it's at the end. And let's compare these two. Okay, well, firstly, I can see that propane is completely symmetrical. That means that it must be nonpolar. That means that the type of intermolecular force over here must also be London forces. We talked about that earlier. Okay, so London forces. Okay, so now they are nonpolar, they are London forces. That means that the intermolecular forces are very weak. Super cool. Okay, propan 1-ol. Okay, so now one of the things that you'll notice in propane 1-ol is it's got this very highly electronegative oxygen over here. It's one of the most on the table. That means that there's going to be a bunching up of negative. It is definitely polar, and that's why you can mix alcohols with water. It's one of the few organic molecules that will readily mix with water, because a lot of organic molecules tend to be kind of like fatty or oily. So alcohols are very polar. They can definitely mix with water. And that means that they've definitely got dipole-dipole, but the strongest force here, because of that OH, is a hydrogen bond. Okay, so hydrogen bonding is way stronger than any of these others. And that means that there are strong forces between the two. So now when you're trying to boil this substance, you have to overcome those hydrogen bonds, and that's how you must word this in your exam answer. Propane is nonpolar, has London forces. These are weak, easily overcome. Propane 1-ol is polar. Hydrogen bonding is occurring between particles of propane 1-ol, and those are much stronger than London forces. So this will require a much higher temperature to be able to vibrate those particles away from each other. So when I'm dealing with an exam question like this, really important to be able to say, okay, well, how many marks is this worth? Now, you can write essays. You can go on for half a page as to why there's a difference between these two. Look at your mark allocation. There's only 3 marks here. All they want is that propane 1-ol has got hydrogen bonding. There we go, hydrogen bonds. There we go, there's 1 mark for that. Propane, London forces. And they want the comparison between the two in terms of energy. So there's 2 marks already. And they want to say, okay, well, hydrogen bonds are stronger than London forces. And that's it. That's all they want to see for those 3 marks. Please don't waste all of your time and energy on these long essay questions. Look at your mark allocation and write to them and say, what are the most important things about my explanation that they want to know? So hydrogen forces are stronger than London, and therefore more energy required. Okay, so before we close out the segments, I just want to leave you with a little bit of a tip when you are practicing your exam questions. Just a note on that, we do have all of the exam papers from the last 3 to 4 years available on our Tenfold app. Please get on that, download it. Make sure that you're taking a look at it. All of the answers are there as well. But now please do not just check at the answers and say, okay, well, here is the memo correct answer for this question. I want you to see if you can see where the marks are allocated, because those give you really good study pointers. I should focus on this because examiners and teachers are looking for this particular thing. When you look at those memos, don't just say, oh, I got it right or I got it wrong. I want to see what my examiner is expecting from me when I do this. It's the biggest mistake I find is that people say, well, I answered it, but did I answer it in a way that it's expected to be marked in the exams? Because at the end of the day, they are going to be seeing that and they don't know me. And they don't know my backstory and how I explain things, so please pay attention to that. I hope you've learned quite a lot this evening, or whenever you're watching this, because we're going to play this a few times. Please make sure that you are keeping up to date with your learning. Keep each other safe. Make sure that you are staying indoors and washing your hands frequently. And goodbye from us.